module number 3, it is two chapters actually. In the first chapter we will be looking the things that is nothing but the scaling factors we will be looking, and in the second module or the second chapter of this module number 3 we will be designing the subsystem design process. So we undergone sort of the general considerations we need to do for the design process, and how the design process will be illustrated with the different test cases we learned. And we have learned one more important concept called as a regularity. And after that regularity, we learned with some of the shift registers implementation. What are the different methods of shift registers implementation we have learned, and we have learnt about the ALU design. There are n number of varieties are there in the design of ALU, starting with a general purpose ALU design, especially the 4-bit adder. In that 4-bit adder, we were carry propagation adder, the carry look ahead adder, and carry skip adder, and general adders, and the modified version of the general adder. So there are different versions of the ALU adders we have learnt in this module. So since you have an internal, so what I thought is so it's better to brush up what are the important things are there, so that it will be easy when you start reading for the internals. Okay, so in the module number 3, the first and foremost thing what and all we have learnt is that is nothing but scaling models and the scaling factors. So in scaling model, what do you mean by scaling model? So if I want to do the miniature size implementation in the VLSI technology means, then I need to go for the scaling model frequently. So depending upon the constraints which has been given by the customers, so either we can go for expansion of the network, or we can go for the constraints, or we can go for the minimum or a minimum cost or a minimum area where we want to implement our circuits. So in such a cases, we want to go for the scaling factors. Then if I want to do this scaling factor means, what are the things I need to consider, or what are the parameters I can go for the scaling. So if I do the scaling, what are the important other parameters will be affected. So all those details you need to understand. So for that we will be studying the scaling models or scaling factors. Okay, so these scaling factors plays an important role in the case of enhancement and also the performance of this VLSI technology, or the performance of the any system you design. It mainly depends upon the scaling model or scaling factors. So when you do the scaling factors, you need to concentrate on the effect of these scaling factors on a different parameters. So here we have taken an NMOS transistors. So for these NMOS transistors, so what are the possible way of we can do the scaling? So it has been highlighted over here. So we have used the two important scaling factors. One we call it as a alpha, and one more we call it as a beta. So if you remember scaling model, that is a parameter alpha, which is responsible for what parameter we can go for scaling with the use of alpha. Okay, so in order to do the scaling for the gate oxide and for the constant voltages, we will be using the scaling factor beta. And for the linear means dimensions, the linear dimensions, it might be vertical or horizontal dimensions. So we will be using a parameter called as a alpha. Okay, so now, so why it is required this scaling is, so all the details whatever I have told, so we will be using. Okay, so the first scaling model what we have used is we have used the gate area. So the gate area is nothing but, it is nothing but L into width of the gate. So since L is a linear dimension and W is a linear dimension, therefore the scaling factor which we use for the gate area, it is nothing but 1 by alpha into 1 by alpha. So it is nothing but 1 by alpha square. So the scaling factor which can be used for the gate area is nothing but it is 1 by alpha square. The second one is gate capacitance per unit area. This will be represented with the use of C naught. So this C naught is nothing but a relativity permittivity between the terminals divided by the gate oxide. So the gate oxide generally we will be represented in terms of D. So since the relative permittivity is a constant, it is a unitless. So the scaling factor D, it is a thin oxide. As I told you, we will be using the scaling factor will be beta, that is nothing but 1 by beta. So therefore, the scaling factor for the gate capacitance per unit area can be given as 1 divided by 1 by beta. So you'll be getting a beta. The next one is the total gate capacitance, how we can calculate. So the total gate capacitance is nothing but area into the unit capacitance. So it is nothing but C naught into L into W. So if I substitute this C naught into L into W, so we know that C naught is nothing but beta, and L into W, just now we have calculated, right, the gate area scaling factor, which is nothing but 1 by alpha square. So therefore the gate capacitance will be 1 by beta divided by alpha square. So similarly the parasitic capacitance will be represented with the use of that is Cx, so which is nothing but Ax divided by D, where D is nothing but a depletion region around the source and drain, and your Ax is nothing but the area of the depletion region around the source and drain. Okay, so since the area, as I told, it is 1 by alpha square, and the distance is nothing but 1 by D, so that is nothing but 1 by alpha. So if I do that 1 by alpha square into 1 by alpha, so what you'll be getting is the answer is equal to 1 by alpha. That is a parasitic capacitance which will exerted or which will exhibit an scaling factor effect of 1 by alpha. So the next one is carrier density in channel Q1. So the carrier density channel Q1 is nothing but C naught into VGS. So VGS is already, we know that it will be beta, and your VGS is nothing but 1 by alpha because it is a constant voltage supply. So we know that the constant voltage supply will be represented or we will be scaled by using a beta. So therefore C naught is equal to beta into 1 by beta. So both the betas will cancel it out. So you'll be getting is equal to 1. The next one is the channel resistance. So the channel resistance, as we know that is a R. R on resistance is nothing but L divided by W. So L divided by, how we can represent? You can represent by the use of the that is the carrier density in channel. We can make use of that and we can represent it is nothing but 1 divided by Q on into mu. Okay, so where mu is nothing but the carrier mobility in the channel. Okay, so this carrier mobility we will be assuming it as a constant because it does not have effect on this channel resistance. So therefore your R on is nothing but 1 divided by Q on into mu. Okay, so we can scale this channel resistance by 1 by alpha divided by 1 by alpha. So alpha and alpha will cancel each other. So you'll be getting 1. Okay, so next the gate delay. So the gate delay is nothing but it is proportional to your R on into TG. So your R on is nothing but 1 and your CG is nothing but beta divided by alpha square into beta divided by alpha square. So this is the scaling factor what you'll be getting for the gate delay. The next one is maximum operating frequency. So the maximum operating frequency of the NMOS device, it is nothing but W divided by L. So which can be written as mu into C naught into VDD divided by CG. So the things whatever we have discussed just now. So if you substitute that, you'll be getting a F naught is nothing but it is scaled by beta square divided alpha square divided by beta. The next one is saturation current, saturation density we have studied, and switching energy per gate we have studied, and finally the power dissipation per unit gate we have studied. So you can see here the power dissipated per gate we can establish, that is nothing but Eg into F naught, and finally we can calculate the scaling factor for the power dissipation per unit area under the area called as PA. So that is PA is nothing but Pg divided by Ag. So with the use of this we can able to calculate all these parameters. So this is the power dissipation product, that is nothing but Pg into Tg. So for this product dissipation product PT, we can write the scaling factor is nothing but 1 by alpha square into beta. Okay, so in summarization we can write scaling factors for the device parameters is nothing but, so you can see for all the parameters, so the combination of Vd and D and the constant E and the constant V which has been highlighted in this table. Okay, so the next we went for the design subsystem. So when we went for this design subsystem, so we need to consider some of the general considerations before we go for the actual design process. So what are those general consideration is, so the design what you are going to establish, it has to provide a unit low cost and it should be higher reliability and low power consumptions it has to be, and better performance and reduced design or development periods. So these are the some of the things what you need to in order to start with the design process. So whatever the design you are going to include, so it should have a low unit cost, higher reliability and low power consumption, better performances and reduced design development periods it should be there. Okay, so the next one is it should have so when you're designing this or when you're considering this general considerations, so some of the problems you are going to arrive. So what are the problems you will be arriving? So the design of complex, some of the problems what you need to encounter during this general consideration is, the first one is how best you are going to design the complex system. So if you have a very large complex system means, then it's the optimum method is to divide this complex system into some subsystem, and these subsystems you can implement it easily, and it will be easy for you to debug also. So once all the subsystem is working properly means, then you can go for the integration, and with the use of this integration we can able to create a complex system. So the next one is the nature of architecture. So before you start for the design process to be implemented, so you should have a what is the architecture you are going to use in the design process. Okay, so how best that architecture will suit so, and what is the different constraints you are considering in order to select that architecture. What are the number of inputs you will be feeding for this architecture, and how many user available slots are there, or if you're using any IC means, then how many number of user slots are there for the accessibility of that IC. So all those things you need to understand, and that will come under category of nature of architecture. The next one is testability. Okay, so once the design has been completed over, so what are the different test cases you will be taking in order to test the design? So that also plays an important role. So that is nothing but testability. So the environment what you are going to consider in order to test your design, and what are the scenarios you are going to consider in order to for the uh, to come up with a better results in the case of design subsystem, you need to consider. So the testability is also plays an important role. Why? Because if the product does not test it properly, and if it sent to the customer side means, then the customers will be having his operations. When he encounters those operations or debug if he find means, then it will be very difficult for the programmer. Why? Because since the subsystem will be working already, and you need to halt that subsystem, and you need to get a request from the users, so saying that the subsystem will not be working under the maintenance time. So during that maintenance time you need to activate your subsystem so that you can reduce that debug. Okay, so these are the some of the design problems what you need to encounter during the design implementation process. Okay, so there are different approaches how you can do this design process. So one of the simple approaches to design the complex of system is to use the divide and conquer method. So with the use of this divide and conquer method, we can able to divide the complex system into unit elements. So the combination of unit elements will constitute a functional block, and these functional blocks will combine and will produce one specific feature of the application. So if you can add all these features, or if you can integrate all these features means, then I can able to design any complex subsystem. Okay, so the approach what it has to be, either you can go from bottom to top approach, or you can go for come from top to bottom approach. So it's not that a hard rule, or it is not saying that from top to bottom approach will provide you a better results when you compare to bottom to top approach. So some applications or some system will require a top to down approach, whereas some certain other applications will require bottom to down approach. Okay, and once you are done with your basic diagram, that is system design, then what are the different approaches are there for you to implement, or what are the different steps are there for you to implement them. So the first step which will be there is a symbol representation, that is called as a logic symbol representation of the given problem. Whatever may be the problem, you need to come up with a logic level representation of that problem. So that complete analysis, or the analysis of this logic symbol problem, is a first step in the several approaches of your design process. The second one is stick diagram. So as we told, the stick diagrams are nothing but a colorful diagrams which are used for the designer to see how best you can design the system with the use of the available software. Okay, so this in the stick diagram, we will be using a polysilicon, we will be using a implant, and we will be using a substrate, we will be using the channels. So how best you are going to make use of this channel and separate all the substrate, all those things is nothing but your stick diagram. So we have come gone through several different versions of the stick diagram. It may be starting SRAM, it may be D flip flop, it may be T flip flops. So there are different stick diagram we can implement with the use of this design process. The next one is the mixture of this logic links and the stick diagram. So if you mix this symbols with the stick diagram means, then we can able to generate the mask layout. So this mask layout we can go for the production, so that we can design the actual architecture block of the system. Okay, so you can see this is the general 4-bit design process for an adder. Okay, so it will be having memory, the ALU content it will be having, control pin you will be having, and the input and output pins you will be having. So the ALU does the simple addition and subtraction, and some logical operations will be done. And in order to store the data, we will be using a memory, and this memory data will be read from the use of ALU registers and also through the use of the control pins. Okay, so the control pins are responsible to have a coordination among the events, so therefore we will be having these control pins. Okay, so this is the general architecture what we have learned. And then as I told you, there will be two types of paths will establish between the embedded system. The first path we call it as a the data path, and the second path we call it as a control path. So in the data path, what we do is the given data we will mainly concentrating on the data path, means how the data will be flowing from one entity to another entity. We call it as a data path. Whereas there is one more important entity which is necessary for us to discuss in the VLSI system, that we call it as a phase part, or it is also called as a control path. This control path enables each device. So what are the things or what are the circuits we should use in order to do the data path controlling and the controlling signals through the use of this means control paths. Okay, so you will be having a data path and you will be having a control path. So you can see here in this operation, that is a data path. So we have a input output operations, we have a ALU bit registers, and this ALU 4-bit registers which is connected from the input and output port through the use of 4-bit shift registers. Okay, and these 4-bit shift registers will be passed through an ALU, and the ALU will does depending upon the status word whether I should go for the right side operation or I should go for the left side operation. So based upon that you will be getting the output. Okay, so this is one of the simple diagram what you can able to expect. Okay, so the next one is for planning of the 4-bit data path. So it's not that only you need to remember the data path only, because the implementation of any circuit will be completed only when the design product is available in hand. So if you analyze during the analysis, if you use the different floor planning methods, then you need to use those floor planning method in order to accommodate your IC. So what do you mean by accommodating of IC? So where exactly I should place this ALU, and where exactly I can pass this bus architecture, that is a data bus and a address bus. Okay, and how I can place this memory component, and how I can wiring how I can do for the interconnection of this ALU. So all those details you need to understand and you need to explain in the floor planning of the data path method. So this is one of the simple diagram what we have used or what we have created, that is a 4-bit shift registers, and the modified version of the 4-bit shifters we call it as a 4x4 barrel shift registers we have learned. Okay, and this is the stick diagram what we have used for the 4x4 barrel shift registers, and this is the mask layout of the 4x4 barrel shift registers what we have used. And I also told that regarding this control pins and the control data and the data bus which is flowing parallelly, you can able to see this the effect of these control pins and data pins, especially in the DSDV subject, that is a data system using very log. So I think you can able to see what is the difference between this data path and the control path. Okay, so this is one of the boundary box for the shift registers what we can implement through the use of this scaling matter, that is a design subsystem process. The next one is regularity. Okay, what do you mean by regularity? Regularity is nothing but it is a total number of transistors on the chip. It is a total number of transistors on the chip. We call it as a regularity. And this regularity, it is nothing but it is a ratio of total number of transistors on the chip divided by the number of transistor circuits that must be designed in the detailed analysis of the implementation. See, in this case, the regularity generally, when we talk about the regularity has to be high for any VLSI circuits. Why? Because the more number of transistors how we are going to place in a unit area, so the complexity, of course, the complexity will be increases, but the compactness of the system will be improved. So with the use of compactness of the system, that is through the use of this regularity parameter, we can able to create a miniature devices with the use of this VLSI technology. So therefore, regularity plays an important role in the case of the design. Is that is nothing but the design of 4-bit ALU subsystem. So in the design of 4-bit ALU subsystem, so we went for the 4-bit data path for the processor. So generally you can see the processor, it is nothing but we will be adder or we will be having some shift registers. So you can see here the 4-bit registers or a processor, it is consisting of an IO port and a data register pins it is having, and 4-bit ALU it is having, and then it is having a 4-bit encounted, that is encoded data around the shift registers. Okay, so this is a general diagram of the processor block diagram. So with the use of this, we have created an 4-bit shift registers. Okay, so this is the design of 4-bit adder. So in the design of this 4-bit adder, we have taken a single adder, that is a single subunit or a single basic unit we have taken, which is add the two given number. Based upon that, we have written the sum and carry expression. So you can see in the given table, it is a 3-bit adder what we have taken. In order to have a controlling mechanism or in order to have a feasibility in the adder circuit, we have made use of the Cin, that is a CK pin as a previous carry pin. So depending upon this previous carry pin, we can generate the sum and carry also. So therefore, your input terminal CK is represented as a previous carry pin. Okay, so this is the truth table for the 3-bit adder. Okay, so and we know that for the with the use of two half adder also we can create a full adder. So the sum expression for the full adder expression is nothing but hk into ck minus 1 bar plus hk bar into ck. Sum and carry expression is nothing but hk into ck minus 1 bar plus hk bar into ck minus 1. Similarly, the carry is nothing but ak into bk plus ak into ck minus bar. Okay, so and we know that the half adder expression for the sum, it is nothing but a bar b plus b a bar. So with the use of that, we can able to create an adder element. And you can see here when ak is equal to bk, we can create sk is nothing but the previous carry what you will be getting. And if ak is equal to b, if ak is not equal to bk means, then we can say that sk is nothing but the sum expression is nothing but the previous carry complement of that. Similarly, for the carry, we can establish a relation that is nothing but when your A is equal to B, your carry expression CK will be either it is AK or it is BK star, or else what we can say that your CK will be the same CK minus 1 value. And if AK is not equal to BK means, then your carry will be CK will be 1 when AK BK is equal to 1, and your CK will be 0 when AK is equal to BK is equal to 0. So these are the relations what we have find between the previous carry and the sum and the present carry output. Okay, so this is one of the simple standard adder element what we will be having. So you can see you have a two input element, that is A and BK, AK and BK, and one output element, that is CK, and we will be using this carry in, that is CK minus 1, either input and output also. Okay, so we have made use of this multiplexer buffered sum with the use of this NMOS technology, and this is a CMOS version of the adder logic. So as we discussed in the class. Okay, and you can see here we can able to create an adder element with the use of CMOS technology. So you can see here we have a VDD and VSS, we have shifted to the left side, so because of the floor planning mechanisms. And we can see here the carry in will be the input for the remaining PWell process and the NWell process, so that you will be getting a sum and carry output in an optimum manner. Okay, so this is the multiplexer cell with and without the cut, and this is a butting contact which is used in the inverters, and these are the buried contacts which we already discussed in the stick layout diagram. Okay, and this is the CMOS inverter design what we can able to design. You can see here we have a contact cuts wherever there is a two different color, means the elements are passing. Okay, so this is the adder element with a boundary box. Okay, and this is how we can create an 4-bit adder. So for each 4-bit adder, so we will having a single bit adder element, that is S0, S1, S2 and S4. So based upon that we can create this adder element. Okay, and this is a 4-bit adder outline circuit how we can create. So you can see here approximately 150 lambda we have taken as a width, and the height, the vertical length we have taken it as a 760 lambda. Okay, so these are the things. So in order to do the simplification, or in order to create a modified adders, so we will be using the sum and carry expression. So if ck minus 1, if it is 0 means, then we know that sum will can be implemented by using a exclusive or, and carry we can be implemented by using AND operation. If ck minus 1 is equal to 1 means, then we can implement the sum expression by using the XNOR operation, and also the carry can be done with the use of OR operations. Okay, so therefore there is a modification in this 4-bit ALU we can able to see. Okay, and then we went for the one more important parameter, that is nothing but the Manchester carry chain. So in the Manchester carry chain, what we have done is, so we have created two functions. One is a propagation function and one more is a generator function. So propagation function is nothing but a exclusive OR operation between the two elements, and your generator function is nothing but it is a ANDing operation between the two input signals. Okay, so you can see here this is the 4-bit, or this is the n-bit cascaded Manchester carry chain elements. Okay, and we have made use of the mux in order to create a carry select adder structure. So this is a 4-bit carry select adder structure. Okay, and one more important thing what we have learned is as carry skip adder. So you can skip some portions of the carry propagation in the n-bit adder. So you can see in the given diagram, so in the first carry when it is generated, we have passed this to 3 cells, and after that we have skipped to 7 cells. So means what, the propagation delay we can able to calculate for the optimum implementation of the adders we can do from the use of this carry skip adder. So you can see here the propagation delay. With the use of this, we can create, that is a maximum propagation delay or the worst case propagation delay, which can calculate from this carry skip adder is nothing but root of 2n k1 divided by k2, where k1 is nothing but the delay which has been encountered by each cell, where k2 is nothing but the delay with which the one subsystem is waiting for the output of the another subsystem. Okay, and you can see this is how we can create the optimization of the carry skip adder, and this is the possible implementation block diagram of the concept. Okay, so the next one we went for the carry look ahead adder. So means the propagative nature of the carry, we can able to establish the carry in well advance. So for that we can create or we can use the propagation function and the generator function. So with the use of this propagator function and generator function, we can create a carry in this manner. So I think we have discussed detailed analysis this. Okay, so we have made use of the exclusive OR operation in order to implement this carry look ahead adder. Okay, so these are the things what you have learned in the module number 3.